In this chapter, we will be learning about logarithms. In this lesson, we will be reviewing the laws of exponents and learning how to solve simple exponential equations. And we will begin by reviewing exponent laws.
So at the beginning of this chapter here on logarithms, we're going to actually start with a review of the exponent laws. And the reason we're going to do that here is because you're going to find very, very shortly here that a logarithm really is just an exponent. Okay? And so a lot of the rules that you're going to look at right here are going to now translate over and become laws of logarithms as well. So you're going to see these guys again here. So let's just quickly go through and review these guys. We'll just zoom in here. So here's an important one. When you multiply two powers together, notice that what we do here is we add the exponents. Okay? So a to the m times a to the n is a to the m plus n. Now, you're going to see in a little while here that it's also good to be able to see this as a to the m times a to the n, like that this can work both directions here. Not only can I put two powers together, but I can split that one apart into two separate powers. Here, division becomes subtraction, right? When you take two powers and you divide them, that's like subtracting the exponent on there. And again, this could also be at one point broken up and you can go backwards and take that subtraction and interpret that as a division between two powers. Here, I've got a power of a power, and so what I do is I multiply those two exponents together. Okay? And so these are ones that you would have looked at a little while ago. You should be fairly familiar with those. So other things that you need to know here, remember that if you've got a times b to the m, I can distribute that exponent through. Now, this rule right here often gets mistaken, and people will do this. Oh, a plus b to the m, that's got to be a to the m plus b to the m. No, that is not true. That is totally not true. This distribution here only works across either multiplication or division here, okay? So if you had, for example, a over b to the m, this would be the same as a to the m divided by b to the m. That also works here, but not over addition or subtraction. Please keep that clear. That is incorrect. Okay, next one here, another one that you should be familiar with here. So if you've got a to the m over n, okay, that is the nth root of a to the m, or another way of writing it is to write the nth root of a all to the power of m. And actually, you're going to find that in a lot of cases, this is a little bit easier to work with. Okay, because it's easier to take the square root to simplify, or the square root to take the nth root first, and then to expand the exponent there. Next, and this is an important one. A to the negative m is the same as 1 over a to the m. The negative in the exponent causes a reciprocal to occur. Okay, man, that's such an important rule. Please remember that. Okay, and likewise, if you've got 1 over a to the negative m, okay, that negative is going to move it to the other side of the fraction here. Or another way to think about it is this is like 1 over a to the m, and when you divide by a fraction, you multiply by the reciprocal and you'll get a to the m out of that. Okay, so just think of it like this. The negative in the exponent forces that term there, that factor, to move from one side of the fraction to the other, one side of the rational to the other. Okay, or if you've got a fraction here, another way of thinking about that negative is that it reciprocates the base. So a over b to the negative m is really the same as b over a to the positive m. Okay, so those are your rules. Now we're going to take a few minutes here and we're just going to apply them.
Simplify each of the following expressions. Negative 16 times a to the negative 6 divided by 20 times a to the 3.
All right, so starting with this guy right here, first of all, I'm going to deal with the coefficients. Okay, so I've got negative 16 over 20. There is a common factor of 4 to both of those, so I'm going to divide out of 4. That's going to be negative 4/5. That's my coefficient right there, okay? Next, I move on to my variables here. I've got a to the negative 6 over a cubed. Remember that division becomes subtraction. Now, subtraction in the numerator here. Now, so watch this. Okay, when I have this rule up here, a to the m over a to the n is equal to, this is like a to the mn over 1. Okay, I got to remember that I'm popping that into the numerator here. Now, there's a couple of different ways I could do this, but I'm going to do this as negative 6 minus 3. Okay, and so this will equal negative 4/5 a to the, well, negative 6 minus 3 is going to be negative 9. Now, there's going to be some emphasis on putting these things in terms of positive exponents. That's not always necessary. Okay, we understand that that is oftentimes just a preference rule. So we're going to bring that down and make this negative 4/5 and then a to the 9 in the denominator here. That a to the negative 9, because remember that was in the numerator, it's going to jump that down to the denominator. Now another way of doing this would have been to think, well, that a to the negative 6, okay, I might have made this negative 4/5. That a to the negative 6 is going to drop down into the denominator, so this will be a to the 6, and then the a cubed is already there. And then when I multiply these two powers together, I simply add their exponents together. That's just another way that you could have thought that one through and gotten the same answer.
Negative 2 x to the 1/3 times y, all to the 6.
All right. Normally when dealing with a problem like this, what I would do is I would follow BEDMAS fairly strictly, and I would look at what's inside the brackets here and do whatever's inside there first. But there's really nothing inside there to do. There's nothing to simplify here. So because these are all multiplied together, I can distribute that 6 through to every term and make this negative 2 to the 6th, x to the 1/3 to the 6th, y to the 6th. Now, negative 2 to the 6th, well, the negative is going to an even power is going to go away. It's going to be positive, and 2 to the 6th will be 64. Sorry. X to the 1/3 to the 6th, I multiply the powers together, the exponents together, and 1/3 of 6 is just going to be 2, and then we get y to the 6th. Actually, that one didn't require a ton of work here, just the knowledge that I'm going to distribute that through, and then again, 1/3 of 6 there is just going to be 2.
Negative 4x squared y to the negative 3 divided by 5x squared y, all to the negative 3.
Now, in this one right here, again, there's parentheses around the whole thing here. I'm going to work on the inside first here. I'll deal with that negative 3 later. So first, I'm going to get negative 4/5. Nothing happened with the coefficients here. X squared over x squared. Oh, I love that. That's great. That's nice. That's just 1. So 1 times 4/5 is 4/5. I'm just going to leave it like that. Now, y to the negative 3 over y, this is going to be y to the negative 3 minus 1. And I know that there are other ways that I could do this here, but for right now I'm going to choose to do it this way. So again, inside my brackets here, inside my parentheses, this is going to be y to the negative 4, and that negative is going to bring it down into the denominator. Okay, now that I've simplified everything inside the brackets, okay, now I'm going to move on to the exponent. There's my BEDMAS, BE, okay? So now this is going to equal, I'm going to move over here. I'm going to run out of room here. Everything here is going to, first of all, sorry, I should deal with the negative. And what the negative is going to do in this case is reciprocate this. I'm still going to leave the negative with the numerator because it doesn't matter where the negative goes, whether it's in front of the full fraction, in front of the numerator denominator. It just looks better in the numerator there, I think. And now everything through here is going to get cubed. So negative 5 cubed, y to the 4th cubed over 4 cubed. Okay, now it's just a matter of doing those calculations. Negative 5 cubed will be negative 125. Y to the 4th cubed, I'm going to multiply those, I'll get y to the 12. And 4 cubed is 64. So my answer here is negative 125 y to the 12 over 64.
Evaluate the following without using a calculator.
All right, so now we're going to just run through these really quickly here. 25 to the 0, now notice that anything to the 0 is going to be 1. So 25 to the 0 is 1. But compare that to this guy right here. This is negative 25 to the 0. Now, based on what I just said here, you might be tempted to say that that's equal to 1, because you'd say, anything to the 0, you just said that's 1. But what's being taken to the 0 here? It's not negative 25. It's just the 25. Had I wanted this to be negative 25 to the 0, I would have to put parentheses around that. That's not what's written here. This is negative 25 to the 0. You have to read that very literally, that 0 only applies to the number in front of it. And this is really like -1 times 25. So this answer here is going to be -1. 25 to the 0 is 1, and then the negative in front causes that to become negative again. This one right here, first of all, I'm going to deal with that negative. Okay, and this is going to be the same as 1 over 81 to the 3/4. And now I'm going to distribute that 3/4 to the numerator and denominator. Now, okay, 1, the 4th root of 1 cubed is just going to be 1. You got to love 1 for that, because 1 just is great to work with. This is going to be the 4th root of 81 cubed. Now, I choose to do it this way because if I put the cube on the inside here, the first thing I'm going to have to do here is cube 81. I don't know what that is. I don't want to work with that. It's like work. But I know what the 4th root of 81 is. Okay, the 4th root of 81 is 3. Now, if you don't know that off the top of your head, it still wouldn't take you long to think about that, because you should recognize 81 is 9 squared. And then from there, that 9 is 3 squared. So like that doesn't take a whole lot to kind of reason that through there. So this becomes 3. And then 3 cubed is going to be 27. So this is going to be 1 over 27. And now finally over here, this question is really about just recognizing what that to the 1/2 means. This is 2 times the square root of 16. Okay, and I know the square root of 16 is 4. And 4 times 2 is going to be 8. And so there we go. We evaluated all those without a calculator.
Convert each of the following to the base indicated. 25 to the 3x to base 5.
Okay, so to convert this to a base 5, what I'm really going to do here is I'm going to recognize that the base here is 5 squared. I know that 25 is 5 squared. Now, 25 is being taken to the 3x. That is going to happen kind of outside the work I'm going to do here. I'm going to replace 25 with 5 squared. So this is still exactly the same as the expression just above it here. So 25 to the 3x is the same as 5 squared to the 3x. And now that I've got a power of a power, I know that I'm going to multiply the exponents together, and this will become 5 to the 6x. That's what they're looking for.
1 divided by 64 to the x to the base 4 of 4.
Okay, so to convert this to base 4, first of all, what I'm going to do here is I don't really want fractions there. Now I know that this, for some people, might not be necessary, but I'm going to rewrite this up in the numerator as 64 to the negative x. And now I'm going to look at 64 here. If I'm being asked to convert that to base 4, that means 64 must be some power of 4. So I'm going to change that 64 to a different form here, but it's going to stay 64. And I'm just going to play with this a little bit, and you should find fairly quickly that that's equal to 4 cubed. And now that I've got a power of a power, I simply multiply the exponents, and I'll get 4 to the negative 3x. And there we go. That's what we're looking for.
4 to the x times 8 to the x to a base of 2.
All right, this one's a little different because now I've got 2 terms here, 2 bases. Okay, so 2 powers here. 4, okay, and I'm going to put these in kind of double parentheses here. 4 is going to be some power of 2. Well, it's 2 squared. 8 is some power of 2. Well, it's going to be 2 cubed. I know that's a little hard to read here, but I want to make sure that we understand that I'm going to replace the base first. 2 squared, 2 cubed. So it's the same thing. 4 to the x, 8 to the x. This becomes 2 to the 2x because I'm going to multiply those powers together. Keep those parentheses. 2 to the 3x. Okay. Now I'm multiplying 2 powers together. What do I do to the exponents if the bases are the same? Well, I add the exponents. I don't multiply the 2 by the 2 here. I mean, yes I do, but I do that by adding the exponents. Okay, a lot of times people get confused and think, well, shouldn't that be 4 to the something? No. If you multiply, for example, if you multiply 3 times 3, this is not 9 squared. 9 squared. Well, okay, because it's like 3 to the 1, 3 to the 1. Well, you don't multiply the bases and add the exponents. You don't do it like that. You just add the exponents together. So 2x plus 3x is going to be 5x. Okay? So and that's the simplified expression that we're looking for here.
9 to the x times 3 to the 4x times 81 to the 2x, all to a base 3.
Okay, so now in this question, a lot more is going on, but it's very similar to the previous one here. Each one of these is going to be a power of 3. So this is going to be some power of 3 to the x. Now this already is 3 to the 4x. That already has a base of 3. I'm good. This one over here is going to be some power of 3 to the 2x. Now I just got to be careful and figure this out here. Well, 9 can be written as rewritten as 3 squared. 81, well, 81 is 9 squared, and if 9 is 3 squared, this is going to be 3 to the 4th. And so now I can multiply the exponents together, so this becomes 3 to the 2x. Didn't have to do anything to that middle term, that was wonderful. But this one over here is going to become 3 to the 8x. Okay, and now I've got 3 separate powers, each with a base of 3. I'm going to add the exponents together. So this is going to become 3 to the power of 2x plus 4x is 6x plus 8x. Well, what's 6 plus 8? 14x. So this is 3 to the 14x.
Square root of 8 times 32 to the x minus 3, all to a base of 2.
All right, now to do this one first here, what I'm going to do is change the radical to an exponent. Okay, so 8, the square root of 8 is going to be 8 to the 1/2, and this is 32 to the x minus 3. Now what I'm going to do is give myself room to change the base there. And again, I'm going to give myself room to change the base here. So now, this right here, 8, actually I didn't really need to do that right in there. I gave myself an extra set of brackets I don't need. 8 as a power of 2 is going to be 2 cubed. Okay? 32 as a power of 2, now you might have to play with that a little bit, but it shouldn't take you long to figure out that that's going to be 2 to the 5th. So now I've got a power of a power inside this set of parentheses. I'm going to do that first. So 3 times a half is just going to be, whoops, sorry, I'm anticipating the exponent. 2 to the 3/2, whoops. Here, power of a power, this will be 2 to the 5x minus 15. Okay, when I distribute that through. Now, it's a very common mistake in a situation like this to multiply the 5 by the x, but not by the negative 3. To forget to distribute that through. But because this is a binomial multiplied by a monomial, those rules hold. You have to distribute that through. And now, because I've got a power multiplied by a power, I'm going to add the exponents together. Well, I've got a 5x here. That's not really common with anything, but I've got a 3/2 and a negative 15. Okay, so that is going to be the same as, well, what's 3/2? This is going to be like negative 30/2. 3 minus 30 is going to be negative 27/2. And so there we go. 2 to the 5x minus 27/2.
1 over 512 to the 4x minus 3 to a base of 2.
All right. So this question right here, a little bit of a bigger base here to work with, but that's okay. Here, when I ask you to convert it to base 2, you can pretty much guarantee that this can be written as a power of 2. Now, first thing we're going to do here is we're going to bring this denominator up into the numerator. So we're going to make this 512, okay, to the negative, now maybe I'll do it in pieces like this, to the negative 1, I'll put the equal sign out here, to the 4x minus 3. So what I'm doing here is I'm reciprocating the base here, the exponent here becomes negative, and now I can multiply that through. So we get 512, and this is going to be to the negative 4x plus 3. And again, I got to keep saying this because I know it's an issue. There's please remember to distribute that negative to both of those terms. Okay, make sure that you don't just put it in the front in that first term, that 4x, and then keep that as a negative. It's got to change here. Now, after a little bit of playing, you should find that 512 is 2 to the 9th. Okay, and so I haven't really done anything here other than identify that 512 is 2 to the 9th. And now, again, I'm going to distribute that exponent through. So this will become 2, what is that, to the negative 36x plus 27. Good, and there you go. That's what that expression would look like as base 2.
27 divided by 64 to the power of x plus 2, converted to a base of 4/3.
Okay, now this one's a little bit more challenging because the base is a fraction here. Now, After playing with these for a little while here, you should notice here that when I ask you to put it says at a base 4/3, I should be able to put this base of this power here, convert it to 4/3 here. But notice that 27 does not align with 4 and 64 does not align with 3. In fact, it's been flipped here. So what I'm going to do here to start off with is I'm going to flip the base here. I'm going to find the reciprocal of it, making that 64 over 27. Now I can do that so long as I make the exponent negative. So I'm going to put a negative in front of the whole exponent, not just the x, the whole exponent here. So right now this is going to be 64 over 27 to the negative x minus 2. Okay, now I'm going to deal with the base here and reducing it down to 4/3 here. So 4/3. Okay, there's my base. I'm going to give myself a little bit of a room for the exponent to the negative x minus 2. So 64, 4, what is that? Good, look at that. They're both cubed. 4 cubed is 64, 3 cubed is 27. Now, if you don't see that right off the top, that's okay. A little bit of playing with that, and you'll see that would pop out for you right away here. So 4/3, and then again, remember to distribute that 3 through, because it's now 3 multiplied by that whole exponent there. So negative 3x minus 6. That's what we're looking for.
We will now start exploring how to solve exponential equations.
Okay, now we're going to move over and start looking at solving exponential equations, which really is the goal for basically every chapter in this course. Is at some point here we're looking at enabling you to solve equations. So we've just taken a little bit of a look at work with exponentials, okay, changing bases and so on. And what we're trying to do right now is use that information to solve some basic exponential equations. Now, this is just our first method for solving these sorts of equations. And what we're going to do here is, and this is the thing you should always look for first. Okay, you should always look for first when you're looking at an exponential equation. And I know that something is exponential because my variable here, we'll zoom in a little bit here. My variable is in the exponent here. There's my exponential equation. What I want to do here first is just see if both sides can be written as the same base, and if that's true, that's what I want to do. Okay, I'd like both sides here to be the same base, because if I've got power equal to power, and that's the whole issue here. If power equals power and base equals base. Okay, so if I've got a power here, I have the two bases are the same here, then here's the trick. Exponent is going to equal exponent. And that's what I use to solve these things. Okay, now this isn't the only method we're going to use. We're going to show you some more sophisticated methods actually in a little while here, a couple lessons. But for right now, this is going to work great for the sorts of questions that we're going to look at right now. So anyway, have a look at the next few problems here.
Solve the following exponential equations. 4 to the x plus 2 equals 64 to the x.
Okay, here we go. We're going to start off with 4 to the x plus 2 equals 64x here. Exponential equation, variables in the exponent. Now I want to look for a common base here. Now there are a couple here because I can see right now that these are both powers of 2. But more easily, and it may be a little bit less obvious, is that 64 is actually a power of 4 as well. 64 is actually 4 cubed. Okay? So I can rewrite that as 4 cubed. Now I haven't done anything. I haven't changed anything. This is exactly the same as it was before. Now what I'm going to do here is I'm going to simplify this expression a little bit. There's not much I can do, but because it's a power of a power, I can multiply the exponents together. And now, because power is equal to power, and the bases are the same, I know that the exponents must also be the same. They have to be. That's the only way these can be equal here. Now, please bear in mind, I'm not canceling the bases. Okay, there is no such thing as an operation that does that. I'm not canceling the bases. What I'm doing is I'm just making a logical little jump here and saying that if these are equal and these are equal, these two must be equal as well. Now bring the x over and we'll get that 2 is equal to 2x. And so therefore, x is equal to 1. And there's the solution to this first equation.
4 to the 2x equals 8 to the 2x minus 3.
All right. In this case right here, I can't get away with making them base 4 each. What I got to do here is recognize that these are both powers of 2, so this will become 2 squared to the 2x, and 8 is 2 cubed, and this will be to the 2x minus 3. And that's great. That's not enough here, though. I need to make this 2 to the 4x is going to equal 2 to the 6x minus 9. And then power equals power, so I'm going to make the exponents equal to each other. There we go. You know what? I'm kind of a lazy thinker here. What I'm going to do is I'm going to bring the 4x over to the right-hand side, make that 2x, and bring the 9 over. I'm doing that just so that I don't end up with a negative in front of the x, okay? Because every time you move things over where there's a negative in front of the x, you introduce the possibility of screwing that up a little bit. So there we go. We'll just leave that like that. And then divide both sides by 2. And so therefore, x is going to equal 9 over 2. And there's our solution.
9 to the 4x equals 27 to the x minus 1.
Okay. Now, you should probably get used to the fact that as we're going through these things, there's going to be a very limited number of options for our bases here. Really, you're looking at like 2, 3, and 5 for the most part. Maybe 7 once in a while, but 2, 3, and 5. So we've done a couple that are base 2, base 4, sort of similar thing here. Now this is, I hope you see it right away, this is base 3. So this will be 3 squared, there's 9 to the 4x. 27 is going to be 3 cubed to the x minus 1. And now I want to say it, I haven't done anything. Kind of keep going back to that. I haven't done anything here because I've just replaced 9 with 3 squared. I've replaced 27 with 3 cubed. But now I'm going to multiply those powers together. So 3 to the 8x. And this is going to equal 3 to the 3x minus 3 because that 3 will distribute to both terms. And now power equals power. Bases are the same, which means 8x must be the same as 3x minus 3. Now, I want to bring these x's over to the side where the x is going to be positive, so I'm going to bring the 3x over, subtract it from both sides to get 5x is equal to negative 3. And therefore, when I divide, I will get that x is equal to negative 3/5. Oops. Apparently classes are starting. There we go. There's the answer.
125 to 6x plus 3 equals 25 to 8x plus 1.
Okay, now here's a question. That's an example of one that's kind of a level up here. Compare 125 and 25 here. Notice that they're both powers of 5. They're both, they both have a common base of 5 here. 125 is going to be 5 cubed to the 6x plus 3. 25 will be 5 squared to the 8x plus 1. Okay? Now, distribute the exponents here. So 5 to, that's going to be 18x plus 9. 5 to the 16x plus 2. And again, just like before, I've got power equal to power. The bases are the same now. So now I can state that the exponents must also be equal to each other to maintain equality. I'll bring the 16x over to the left-hand side because I know that that's going to give me a positive in the value in the front here. And it's going to be a nice number here, 2. Subtract the 9 from both sides, I'm going to get negative 7. And so now when I divide out that 2, I'm going to get negative 7 over 2. And there's my solution.
8 to the x plus 2 equals 1/4 to the x plus 3.
All right, back to 2 here. Because I see the 8 and the 4. It's got to be powers of 2 here. So 2 cubed and 8. This is up to the power of x plus 2. So 2 cubed to the x plus 2. Now 1 over 4 though. Now I know 4 is 2 squared. I know that. But this is 1 over 4. So because the 4 is in the denominator, this has actually got to be negative 2 to the x plus 3. I just got to remember that negative in there to deal with that. Now I'm going to distribute my exponent through. So 2. That'll be to the 3x plus 6. This will be 2 to the negative 2x minus 6. Power equals power. Bases are the same, so the exponents must be the same. Okay, now again, I'm going to bring everything over so that my x terms are positive. So I'm going to bring the 2x over. It'll become 5x. And I'll subtract 6 from both sides to get negative 12. And then I'll divide, and I'll get x is equal to negative 12/5. Kind of an ugly little fraction there, but hey, it's good. It's good.
5 times 3 to the x equals 135.
Okay, this question here is a little different. When you look at this right away here, looking for a common base here, I'm not seeing anything here. But what I should be doing first though is isolating the power. Okay, I should be getting the power by itself if I can. So I've got this 5 out front here, so I'm going to divide both sides by 5. And when you divide 135 by 5, you're going to get 27. Okay, so this is a much simpler equation here. And notice that now I've got two expressions here that can be written with the same base. 27 is 3 cubed. Now in this particular case right here, this is actually a very straightforward question because this is 3 to the x is equal to 3 cubed. The bases are the same, powers are the same. It means the exponents must be the same. But as soon as I've done that, I've answered the question. I'm done. X equals 3. Okay. Please, when you see something like this, do not make this 15 to the x. Okay, remember bed mass. Remember order of operations. I would have to deal with the exponent, okay, before multiplication. I would have to deal with 3 to the x before I could multiply 3 by 5. So that is, if you're doing that, you're doing bed mass in the wrong order here. You're not applying the order of operations correctly. It's an easy fix. Okay, just be aware that that is an issue here.
3 to the 4x times 3 equals 27 to the 2x.
Okay, now we're starting to step it up a little bit here because there's a little bit more going on in this problem. Okay, now I'm going to do a couple of things in this first step here. Notice on the left-hand side that I've got a power of 3 multiplied by a power of 3. Well, when I do that, I add the exponents. And remember that if there's no exponent written on a power here, the exponent is 1. So in my exponent here, I'm going to have 4x plus 1. Now on the right-hand side, I'm simply going to write 27 as 3 cubed. And so now I get 3 to the 4x plus 1 is equal to 3 to the 6x. Okay? Power equal to power. Bases are the same. I know that my exponents must be the same. Again, I'm pretty lazy. I'm going to bring my x's over to where they're positive. So I'm going to subtract the 4x over here, so make that 2x. This is equal to 1. And then I will divide by 2 and get that x is equal to a half. There's my solution right there. I know that a lot of people don't particularly like it to have the x on the right-hand side, but it doesn't matter. It doesn't change anything because we're still got this equality statement here. So it's still good.
4/7 to the 5x equals 64 over 343 to the 2x minus 1.
Okay, now in this question here, the difficulty level is increased a little bit just because we're throwing fractional bases in there. But that's it. That's all that has happened here are the fractional bases here. Now, take a look at these numbers here. 4, 64, 7, 343. Okay, they're related to each other. Okay? 4 does correspond to 64, 7 does correspond to 343. So there's been no reciprocating here. And I have to look for that because that is an issue. Okay, so I just wanted to be aware of that. Now, 64 and 343, these are both going to be, this is going to be 4 over 7 here, and that's going to be cubed to the 2x minus 1. Now that might take a little bit of kind of playing with on your part here. You might have to kind of plug those numbers in your calculator and just double check that. But that's going to be true here. And not only that, they're going to be to the same exponent. Okay? In order for this to be a question that can be solved efficiently, we have to give it to you where this base and this one right here, like the 4 and the 7 here, they're going to be roughly the same. So they're going to be the same exponent. It just makes these things a little bit easier to solve. It is possible that they are different, but then that's going to really increase the level of difficulty here, and we're really not interested in that at this point. We want to take this a different direction in a few lessons here. So, okay, first of all, I got to expand out the exponent on the right-hand side here. So this will be 4 over 7 to the 6x minus 3. Okay, now power equals power. The bases are the same, so I know that the exponents must be the same. I want to bring the x's to the side, whatever side is going to make them positive, so I'm going to bring them over to the right-hand side. So subtract 5x from both sides, and I'll add 3 to both sides. So x is equal to 3.
1/9 to the x equals 27 to the x divided by 9 to the 2x minus 1.
Okay, whole lot going on in this one, and you got to be careful with this one. We did something sort of similar a few questions ago. There's an idea that's going to pop out here, but we got to be careful here. Now, notice between 9 and 27, the common base here is going to be 3. This is going to be 3 squared to get 9, but because the 9 is in the denominator, I'm going to make that 3 to the negative 2. Now, so those two bases are exactly the same. 3 to the negative 2 is 1 over 9. Over here, 27, I'm going to rewrite as 3 cubed to the x. And 9 down here is going to be 3 squared to the 2x minus 1. Now, I'm dividing two powers here. At some point, I'm going to want that to kind of change into a subtraction. But I need the bases to be the same before I can do that. So that's the one little trick here, and it makes this question a little different than one that we did before here. So this is going to be 3 to the negative 2x. That's not a problem there. Just multiply the powers together. This will be 3 to the 3x over 3 to the, what do we got here? We're going to distribute the 2 through, so it'll be 4x minus 2. Now, I'm going to just keep going here horizontally here because I'm going to play with this right now. The equality is going to stay, but I'm dividing powers here, which means I'm going to subtract exponents. So I'm going to subtract 4x minus 2. So I'm going to subtract the 4x, and I'm going to subtract the minus 2. I'm subtracting the minus 2. Got to be really careful about that. It's going to be really tempting to just put minus 2 there, but actually that should be plus 2. Okay? Because I'm subtracting, okay, this division here tells me to subtract that full exponent, subtract the 4x, subtract the negative 2, positive 2. Now, this is now 3 to the negative 2x is going to equal 3 to the power negative x plus 2. Powers are the same, bases are the same, which means my exponents must be the same. Okay, now I'm going to move things around so that I want my x to be positive. So I'm going to add the 2x to both sides. So that's going to make that x on the right-hand side. I'm going to bring the 2 over, so x equals negative 2. All right, and there's the solution.
27 to the x plus 2 equals 1/3 to the 3 minus 6x.
Okay, well, we've already worked with bases that look like this, so we already know what to do here. 27 and 3, they both are powers of 3. So 27 is going to be 3 cubed. This will be to the x plus 2. My base here, granted I'm seeing a 3 in it, but right now the base isn't 3, not in that power. The base is 1/3. To bring that up, I got to make this 3 to the negative 1. They're the same thing, but now this is written in the numerator. It's written base 3, and I can deal with the exponent in just a second here. So now that I've got 3's in both cases here, I can just distribute the exponents through. So this will become 3 to the 3x plus 6. And this will be 3 to the power of negative 3 plus 6x. I got to remember to distribute the negative through to both terms. Now, power equals power. Bases are the same, which means my exponents must be equal. I'm going to move things around so that my x value is positive, so I'll subtract 3 from both sides, the 3x, so I'll get 3x on the right-hand side. And I'll add 3 to both sides to get 3x is equal to 9, 9 is equal to 3x. Divide both sides by 3, and we get the solution here, that x is equal to 3.
4 times 9 to the x minus 1 equals 108.
Okay, now this one, similar to one that we've done earlier, this one looks a little odd. Okay, because I'm looking for a common base here. Well, between 4 and 9, there is no common base. Okay, 4 is 2 squared, 9 is 3 squared. But what I should be doing here is trying very hard to isolate the power if I can. Now, in some cases, in some of the previous cases, like for example, this question over here, to get this power kind of isolated, basically because they had the same bases here, I just multiplied those together to get a single power. Here, what I'm going to do is I'm going to divide both sides by 4. And that'll get me 9 to the x minus 1 is equal to 27. Well, I like those numbers. I've already worked with those several times. 9 is going to be 3 squared, still to the x minus 1. And 27 is going to be 3 cubed. Distribute the exponent through, so 3 to the 2x minus 2 is equal to 3 cubed. Power equals power, so the bases must, sorry, and the bases are the same, so the exponents must be the same. Bring the 2 over, just add that 2 to both sides here. We'll get 2x is equal to 5, and then divide x is equal to 5 halves. There's my solution.
1/16 to the x plus 2 multiplied by 4 to the x minus 3 equals 8 to the 2x multiplied by 4.
All right, now this one's got a lot going on with it. But look at the bases here, 16, 4, 8 here. All of these are powers of 2. So 16 is going to be 2 to the 4, but it wasn't just 16, it was 1 over 16. So to get the sense of that reciprocal here, I'll put a negative in the exponent. This is still to the power of x plus 2. Multiplied by, this will be 2 squared, whoops, sorry, to the x minus 3, okay, is going to equal, 8 will be 2 cubed, okay, and this will be to the 2x, multiplied by 4, which will be 2 squared. So now everything has been written as a power with a base of 2. Now I got to deal with the exponents. And it's going to take me a couple of steps here because there's a lot more going on in this question than there has been in some of the previous ones. First of all, I'm going to distribute here. So this will become 2 to the negative 4x minus 8 when I distribute that negative 4 to both those terms, multiplied by, again distribute that 2 through, so this will be 2 to the 2x minus 6. On the right hand side, I've got power of a power here, so I multiply the exponents, 2 to the 6x. And then over here, actually there was nothing I could do with that one. 2 squared is just 2 squared. So I've dealt with the exponents. Now I'm going to deal with the multiplication here. And when you multiply powers, what do we do to the exponents? We add them. So negative 4x plus 2x will be negative 2x. Negative 8 and negative 6 will be negative 14. On the right hand side, this will be 2 to the power of 6x plus 2. And now, after a fair bit of playing around with this, I've got it down to a power equal to a power. The bases are the same, so therefore my exponents must be the same. And now it's just a matter of solving for x here. And I'm going to bring everything over so that my x term is positive, so I'll add 2x to both sides to get 8x. I'll subtract 2 from both sides to get negative 16 on the left hand side, and then just divide to get that x is equal to negative 2. Ah, that was a good one. A lot of work for that one. Excellent.
Solve the following equations that contain rational exponents. X to the 1/3 equals 5.
Okay, now we can't go looking at exponential equations without taking a few moments to look at these kind of equations that have rational exponents here. Now, the issue here is, and it's very tempting, especially once you've solved a whole bunch of exponential equations. It's tempting to do this wrong or to look at this and say, man, I have no idea how to solve this. How do I make x and 5 the same base? The issue is you don't. This isn't an exponential equation. The variable here is in the base, not in the exponent. This is not an exponential equation. You've solved questions like this before. What we're going to do here is we're going to do the exact opposite of what this is saying. This is saying that the cube root of x is equal to 5. Well, what's the opposite of cube rooting something? Well, cubing it. So what we're going to do is we're going to raise both sides of this equation to the reciprocal power here. So this becomes x to the 1/3. Now I'm going to do this in steps like this for this particular question here, but we'll do it a little bit quicker later on here. Because when I do it like this, when I raise it to the reciprocal power, 1/3 of 3 is just going to become x to the 1. That's what I want. I want x equal to some value here, and 5 cubed is 125. So there's the solution to that specific equation.
X to the negative 4/3 equals 81.
Okay, so in the spirit of the previous question here, remember, this isn't an exponential equation. The variable is in the base. So what I'm going to do is I'm going to raise both sides of this expression here to the reciprocal of that exponent on the x. So this will be to the negative 3/4. Now notice I didn't say we were going to change the signs. Okay, I'm not raising this to the positive 3/4. I'm raising it to the reciprocal of this, and the reciprocal doesn't change the sign, so it's going to stay negative here. So on the left hand side, this is going to end up becoming x to the 1. On the right hand side, I'm going to get 81 to the negative 3/4. Now, what that means, first of all, the negative implies 1 over. The 4 means this is going to become a 4th root of 81, and the 3 means cubed. Okay, here we go. Well, what's the 4th root of 81? Well, if you don't know off the top of your head, let me help you out with that. It's going to be 3. Cubed is 27. So the answer here is going to be 1 over 27.
5 times x to the 2/3 equals 45.
Okay, now for this one right here, same sort of thing. Remember, the variable is not in the exponent, it's in the base. Now, I do want to raise both sides of this expression here, this equation here, to the reciprocal power. But before I do that, I want to isolate the power. Right now, the power's got a coefficient here of 5. 5 is not being taken to the 2/3. It's just the x. So I'm going to get rid of 5 first. So I'm going to divide both sides by that 5. So that will get me x to the 2/3 is equal to 9. Okay, now the term, or the factor with the x in it has been isolated. Now I'll take it to the reciprocal power. On the left-hand side, that's going to get me x to the 1. On the right-hand side, that's going to get me the 9 to the 3/2, which is going to be the square root of 9 cubed. Okay, the square root of 9 is 3. Cubed is 27. Now, I do it in that specific order because I'm kind of lazy. I could do this as 9 cubed and then square root it. But off the top of my head, I don't know what 9 cubed is. I mean, I do, but it's so much like work. And then to figure out the square root of that, it's so much easier to reduce that down as much as I can and then build it up again by applying the square root first and then the cube. It's just easier.
3x minus 2 all to the 3/5 equals 8.
All right, now, don't let yourself get thrown off by this one here, by the fact that it's got a binomial base here. This is still base to the 3/5 equals 8. My goal is to isolate the power. Okay, in the previous question there was something else that I had to do to isolate that power, but in this one, the power's been isolated. Don't let the fact that the base is a binomial throw you off. That's totally okay. It's still power equals power here. So I'm going to raise both sides to the reciprocal power here. Now on the left-hand side, that's just going to leave me with 3x minus 2. On the right-hand side, I'm going to get 8 to the 5/3. Now let's deal with this first here, okay? And I'm going to do the cube root first because I know the cube root of 8 is 2. And then 2 to the 5th is 32. And I haven't done anything to the left-hand side, so it's still there like that. So now I'm going to bring the 2 over. So 3x is equal to 34 because I have to add 2 to both sides. So x is equal to 34 over 3. There's our solution.